we're going to be talking about conservation of momentum. So we're going to be looking at collisions and crashes today, and this idea of what happens right before and then right after a collision. So the big question is, when can we say momentum is conserved? That is, that it remains constant. So if we have an isolated system, so a system with no outside forces, two things impacting each other, then we're going to say momentum is conserved. And then we can say momentum is conserved if we have collisions, because we're just going to focus on the system before and the system after, so we can ignore the friction. And then the other time when we have momentum conserved is when objects start at rest and then push away from each other. So again, starting at rest where we have like no momentum, and then pushing away from each other, so one object and another object go in opposite directions. So here's the law of conservation of momentum. It says in an isolated system, the total momentum of all objects interacting with one another remains constant regardless of the nature of the forces between the objects. So as long as we're talking about an isolated system, the total momentum of one object interacting with another remains constant. So in other words, the initial and final momentum are equal. So the initial momentum, the final momentum, they're equal to each other. So P initial equals P final. And notice they're bold, so they need little vector marks. So these are vectors. So that leads us to formulas with the conservation of momentum. So let's look at this green one first. Two objects collide and then bounce off of each other. So I have the mass of one object and the velocity of that first object initial. And then I have the second object, whatever is colliding with the first object. I have its mass and its initial velocity. So this is the initial state, right? Before the crash. Then I have after the crash, directly after the crash. I have the mass of object 1, and then this is going to be my final velocity of 1, plus the mass of object 2 times the final velocity of 2. Right? So it's the total momentum in the system, right? So here's my total momentum. Right here is my total momentum initially has to equal my total momentum finally. So the momentum of object 1 plus the momentum of object 2 initially has to equal the momentum of object 1 final plus the momentum of object 2 final. Okay, let's look at this weird situation where two objects collide and then they stick together. So oftentimes in collisions and accidents and crashes, you have one object colliding into another and they actually move together. So we have them as separate objects in the beginning. So you have the mass of one and you have the velocity of that same object, but it's its initial velocity. Then you have the second object that it's about to collide with and its initial velocity, velocity 2 initial. But once they stick together, now I have the mass of 1 plus the mass of 2, right? Because these are stuck together. So their masses move together at the same velocity. So when two objects stick together, they end up with a final velocity that's combined because their masses are combined. So then we can look at it like that. Oh, look, it's the same. We add the masses. They're going at the same speed. So it's just mass 1 plus mass 2 times the final velocity. And both of these are on your equation sheet. Okay, let's try this one. If a reckless ice skater collides with another skater who is standing on the ice, is it possible for both skaters to be at rest after the collision? So let's think about this for a sec. We got one person standing still and one person is like skating towards them in complete peril, completely collides with them. Is it possible for them to both be at rest after the collision? Well, let's look at this from an equation standpoint. So I have the mass of the first person and the velocity of the first person initial, right? So this is the person that's colliding into them. The other person isn't moving. So do they have momentum? No, they have no velocity, right? Because the momentum would be, this is the mass of the second person, velocity to initial. They're not moving, so this is 0. Okay, so I have to have some momentum over here. The question is, could this be 0 and this be 0? And the answer is no. I have a quantity over here, so one of them has to be moving. Oftentimes, it's not the person who collided into them. Sometimes they will transfer their energy and the other person will go sliding. So it just kind of depends, but they can't both be at rest, right? One of these two individuals needs to have some sort of velocity in order for you to have a quantity over on this side. So maybe it's this person, or maybe it's this person, or maybe it's both, but they can't both be at rest because I have that initial quantity. So this is impossible. Let's try another question. How does a rocket change its velocity in empty space when there's nothing for the rocket to push against? So we watched a video of astronauts trying to do some simple mechanical tasks in space, and they couldn't do it, right? Because they weren't thinking about, for every action, there's an equal and opposite reaction. So we have nothing to push against. So how is it that we can do this? Well, if I have a rocket ship right here, here's my very fancy rocket ship. Yep, rocket ship. If I need this rocket ship to go forward and it's starting from rest, what I can do is use a force in this direction, right? So if I apply a force by causing an explosion that goes this way out of the rocket, since the rocket started at rest, right? And then I'm going to cause this little explosion in that direction, that's going to make the rocket go this way, equal and opposite, right? So I can shoot out some sort of an explosion, some sort of fuel, and propel myself forward by having an explosion go in the opposite direction. Right? So this is how we can make things work in space, or how rockets can go in space. I think we're ready for some problems. All right, so we're golfing. The head of a 215-gram golf club travels at 55.0 meters per second just before it strikes a 46-gram golf ball at rest on a tee. After the collision, the club travels in the same direction at 42.0 meters per second. What is the speed of the golf ball just after impact? Okay, so we have a lot of things here, and I'm going to kind of use a lot of subscripts to try to abbreviate this. So I have mass of the club here is, and I'm going to put it in kilograms, 0.215 kilograms. Okay, and then I have the initial velocity of the club is, I'm told, 55. Oop, change color on it there. 55 meters per second. And I'm also told that I have mass of the ball is, again, converting to kilograms, don't forget, 0.046 kilograms. And the initial velocity of the ball is 0. I know that the final velocity of the club is 42, but what I don't know, my unknown, is the velocity of the ball final. Okay, so using this equation, I'm going to say, all right, I have my momentum final, and it has to equal my momentum initial. So momentum mass of the club times velocity initial of the club plus mass of the ball times velocity initial of the ball. There's my two momentums, has to equal mass of the club times velocity of the club final plus mass of the club times velocity of the, mass of the ball times the velocity of the ball final. Do we see why Mishop has a lot of abbreviations? This gets crazy very quickly. So it helps to put all the superscripts in. All right, I'm going to cancel things I know out. I know that the ball is not moving, so that's what I'm going to start with there. Okay, now I'm going to pause it and erase the board a bit so that I have a little bit more room. Okay, so I moved my equation up to the top so I have a little bit more room. And let's plug all of this in. So the mass of the club was 0.215 kilograms. The initial velocity of the club was 55 meters per second. And then the initial velocity of the ball is not moving, so I got nothing, no momentum there. And then I have, again, the club here, 0.215 kilograms times the final velocity of the club. Notice it's in the same direction. The direction is going to get very important on this because it's the same direction. I get to keep the positive sign and I don't have to think about a negative sign, which is nice. And then I have the ball, which is 0.046 kilograms times a final ball velocity. All right, so I'm going to multiply these together and I get 11.825. And then I'll multiply these together and get 9.03 plus 0.046 V. So I'm going to subtract 9.03 from each side and get 2.795 equals 0.046 velocity. Divide both sides by 0.046, and I end up with a velocity of, so put it up here, I think on my calculator I got like 60.76 meters per second. That is definitely not the right number of sig figs, so it looks like I have 333, so 8 meters per second. And there is my final answer. Notice it's positive, so that means that the ball is going in the same direction of the club, which if you think about golf, makes sense. Okay, so let's try another problem here. So I'm going to start with my givens. Even before I'm reading, I'm just like, oh, let's write some stuff down. So I have the mass of a car is 2,150 kilograms. And it's moving east. Velocity of the car is 10.0 meters per second. And it collides and joins with another car. Okay, so I guess this is car one, and this is its initial velocity. So then I say the mass of the other car, we'll call that car 2, is 3,250 kilograms. And they move together. Okay, they're going to be stuck together. And there's a final velocity of 5.22 meters per second. And it's asking me, hey, what's that velocity initial of that second car? So car 2's initial velocity. All right, so I have to take the momentum of both cars to begin with. So I know that it's the mass of car 1 times the velocity initial of car 1 plus the mass of car 2 times the velocity of car 2 initial. And then they get stuck together. Okay, so I have one car crashing into another car, and the two cars move together as one. So that means the mass of car 1 plus the mass of car 2 times the final velocity, right? Because they're moving together. So, okay, let me plug this in. 2150 times, and yes, I dropped my units, but I'm going to run out of room, so that's why I dropped my units. Okay, 3,250 times, I don't know. equals 2,150 plus 3250 times 5.22. Okay, so this is just 21,500 plus 3250. I'm just going to say velocity now, initial, just to keep it straight in my head. These together, let's see, that's 5,400 times 522, 5.22. If we do it all in one step, that's 28188. Okay, I need to subtract 21,500 from both sides. And I'm left with 3250 initial velocity equals 6688. If I divide both sides by 3,250, I get initial velocity of, see, I'm going to do my sig figs, 2.06 meters per second. And there we go. So the trick about this one was when the cars collide, they stick together. All right, so now we have this new situation where I have two things that aren't moving. And then one thing moves in one direction, and then somehow there's some sort of reaction where one part of it moves in one direction and part of it moves in another. So if I start from rest, right, the two objects have to have their momentums cancel out essentially. So I end up with a total of 0. So let's kind of take a look at how this type of problem works. So what I have here is I have a shell. So we're talking about a rifle, and we're talking about using a gun. So we have a mass of 0.050 kilograms. Yeah, that's right, I converted. So that's the mass of the shell itself, which is what goes into the rifle, is fired from a rifle with a mass of 3.00 kilograms. And the shell, because I'm using my English here, fired from that's a prepositional phrase. So the shell has a speed of 400 meters per second. All right, with what velocity does the rifle recoil in the opposite direction? And if you have fired a rifle before, you know about this. If you have not, the rifle will actually go backwards into the body of the person shooting it. So this is something that happens. So what we want to know is, what is the velocity of the rifle? And again, these are finals velocities. Okay, so I know that the shell and the rifle are not moving to start off with. So yeah, I could sit here and say mass of the shell times velocity of the shell plus mass of the rifle times velocity of the rifle initial. But these are 0. So they're not moving at all. So I have 0 has to equal my mass of my shell times my velocity of my shell final plus my mass of my rifle times my velocity of my rifle final. Okay, so that's a big fat 0 has to equal this. So mass of the shell, 0.050 kilograms times 400 meters per second plus 3.00 kilograms times this velocity. Okay, well, 0.05 times 400, that is 20. Plus 3v. I'm going to keep it real simple here. All right, so that means I need to get the v by itself, so I'm going to subtract 20 from both sides. So I have negative 20 equals 3v. So then I'm going to divide both sides by v, or 3, And when I do, I have velocity equals, and don't forget that negative, 6.67, because I need 3 sig figs, meters per second. So the bullet is going to go forward, right, at 400 meters per second, but the kickback of the rifle is going to be 6.67 meters per second into the person shooting the gun in the opposite direction, which is why we have that negative there, which is super important. Let's try another. Okay, so last one. A mass of 44 kilogram student, use that as an S, on inline skates is playing with a exercise ball. This is actually fun, slightly dangerous. So this is the mass of the exercise ball is 22 kilograms. The student is holding the ball and the both are at rest. So initial 0, initial 0. The student then throws the ball horizontally, causing the student to glide to the right. Right means positive. So the student's final velocity is going to be 3.5 meters per second. What velocity is the ball when it is thrown? So what I'm looking for is velocity of the ball final. Okay, nothing's moving in the beginning. So you know what? I'm not even going to mess. I'm just going to say 0. I have nothing moving, so I have no momentum. But then when I throw the ball, I get momentum. The mass of the student times the velocity of the student final plus the mass of the ball times velocity of the ball final have to equal this 0. So, okay, I have 44 kilograms times 3.5 meters per second plus 22 kilograms times, I have no idea. Okay, so 44 times 3.5 equals 154. So 0 equals 154 plus 22. Again, I'm going to be simple and write just V. So I'm going to need to subtract 154 from both sides, which is going to equal, if I put it over here, negative 154 equals 22V. So if I divide both sides by 22, I end up with V equals a negative 7.0 meters per second because I need 2 sig figs. So again, the ball will move in one direction and the student will move in another. So that negative is crucial for this. Okay, now you can go ahead and start working on your problems from the book.